Welcome to the last day of our seminar series on biomedical applications. So today in the morning we have two talks, and the first speaker is Dr. Ivar Kriben. I suppose it's Ivar, right?
Ivor.
Ivor.
Yes.
Sure. Right. It's like Ivan. Well, I see. Right. So we're going to talk about methods for detecting change points about by stringent fMRI and financial data. Right. Please welcome.
Okay, so firstly, thank you very much for the invitation. So I'm going to talk about graph-based change points, but it could also probably be called network change points, or in fMRI, functional connectivity change points. So I know we talked about fMRI yesterday, but for those who wasn't here yesterday and don't know about fMRI, I'm just going to give you a few slides on fMRI. So functional magnetic resonance imaging, it's a type of specialized MRI scan. It's a non-invasive technique for studying brain activity, and over the course of an fMRI experiment, a series of brain images are acquired while the subject performs a set of tasks or changes psychological state. Okay? And then changes in the measured signal between individual images are used to make inferences regarding task-related activations in the brain. So the way I like to see it is the brain as a big cube. And then within that cube, you've got a lot of smaller cubes, which are called voxels. And they're about 3 millimeters by 3 millimeters by 3 millimeters. And then during the course of an experiment, we get several hundred images are acquired, say 1 every 2 seconds or so. So within each small cube or within each voxel, we get a signal. So you can see this as a time series problem. So for one voxel, we get one time series. And then what usually happens is we define some independent variables, and we fit a regression to each of the voxels, or each voxel's time course. So human brain mapping, it's been primarily used to construct maps indicating regions of the brains that are activated by certain tasks. So you've all seen maps like this before. So during certain tasks, certain regions of the brain or certain voxels are activated. However, in order to understand the inner workings of the brain, people have been moving towards connectivity studies. So recently there's been an increased interest in augmenting this type of analysis with connectivity studies. So people have defined what functional connectivity is. It's the undirected association between 2 or more fMRI time series. Okay, so some sort of dependence measure. So to measure this functional connectivity, we could use, say, a covariance, correlation, or precision matrix between predefined regions of interest. So a region of interest is just an amalgamation of voxels where we just average each of the voxels' time course. Or between a seed region, so we could estimate the covariance, correlation, or precision matrix between a seed region and other voxels throughout the brain. Okay? So once we estimate a covariance correlation for each of the voxels, these are typically applied to steady state time series data. Okay, so where the experimental condition is not changing over time. They do not consider the possibilities of changing functional connectivity or the dynamical nature of interactions between the brain regions. Okay? So therefore, we introduce this technique, which we call dynamic connectivity regression. So it was motivated by the fact that under certain circumstances, the dynamic manner in which ROIs, or these regions of the brains, interact or communicate over the course of experiment is in fact of primary interest. Okay? And again, it's motivated by the fact that often it is difficult to specify the nature, timing, and duration of these psychological processes a priori, so before the experiment. And finally, if the dynamic connectivity between the ROIs is not taken into account, we do not capture the true dynamics, and the overall connectivity is just some sort of average. Okay? So we introduced the dynamic connectivity, which I might refer to as DCR at some stage. So it's a data-driven technique for partitioning the experimental time course into distinct intervals based on the underlying functional connectivity patterns between ROIs. So it's a 2-step procedure, okay? So DCR, first of all, takes the functional connectivity change points. And then once it detects the change points, it estimates a graph or series of relationships between each pair of change points, okay? So you can think of this as, say, a graph-based change point detection. So this plot or this figure sort of encapsulates what we're trying to achieve, okay? So assume that you have, say, 15 ROIs or 15 time series represented by the vertices. And you can see that the connectivity is changing over time. The dependent structure, the edge structure is changing over time. So what DCR, first of all, it would like to detect where the change points or the graph-based change points are happening. So it would first detect where row and new are, okay? And then once it estimates where row and new are, it'll then estimate graphs between each pair of change points. So between 0 and row and new, and row and t. And hopefully we do a good job of estimating connectivity structure, okay? So a motivating example, so some experimental data which I will return to at the end of the talk. So we have data from 26 participants, and they were told they'd be given 2 minutes to prepare a 7-minute speech, okay? I'm sure lots of you have seen this data set before. So they were told to be given 2 minutes to prepare a 7-minute speech, but the topic would be revealed to them during the scanning, okay? And then after completing the scanning session, they would have to then deliver the speech to an expert panel of judges, okay? So this diagram at the bottom is a nice summary. So the subjects go into the scanner for 2 minutes, they're resting for 2 minutes, anticipating what the topic is. And then on a little visual screen inside the scanner, they're told the topic. On the topic in this case, it was why you were a good friend. Not a great topic. And then they have 2 minutes to prepare a speech. And then at the end of those 2 minutes, they were told on the little visual screen again that they don't have to give the speech at all. And then they rest again for 2 minutes, okay? So what we're interested in is how the functional connectivity changes as the subject moves from resting to anxious or stressed, back to resting again. And obviously the two resting periods are not quite the same, because before they're anticipating, they're probably a bit anxious already, and after they're really relieved, okay? So again, I'll return to this data set at the end. So there's some background on graphs and precision matrices. So a graph displays the dependency structure of a random vector y. In our case, it's going to be a set of brain regions using a graph G. So it's made up of edges and vertices. So a graph of y can also be represented by the precision matrix, which is the inverse covariance matrix of y. A missing edge between two vertices in the graph indicates conditional independence between the variables, giving rise to a zero element in the precision matrix. And in the fMRI setting, which is our case, a missing edge is seen as is indicating a lack of functional connectivity between these brain regions, okay? So how are we going to estimate the graph? Well, one way to estimate it is the graphical lasso. So the graphical lasso, or GLASSO, was introduced by Friedman, Hastie, and Tibshirani in 2007. And it's a method to estimate sparse graphs or precision matrices. And so what it does is it shrinks elements of the precision matrix to 0, and in our case, which correspond to missing edges in the graph. And it's obtained by minimizing the penalized log likelihood. So the parameter of interest is this lambda here, okay? So this lambda controls the sparsity of the graph. So if lambda is very large, then the graph is sparse, there's not many edges. If lambda is quite small, it's a fuller matrix with lots of edges, okay? So the question is, which we'll come back to, is how do we choose lambda, okay? So the general setup of DCR method is as follows. So suppose we have x1, y1 up to xt, yt. So it's an IID sample from the joint distribution of x, y, where x is a d-dimensional and y is a p-dimensional random vector. So y is just going to be our data from the p ROIs. It assumes that y given x is normally distributed with a p-dimensional vector valued mean function and a p by p matrix valued covariance matrix, okay? So the goal in DCR is to find a sparse inverse covariance matrix omega hat for any x in the domain of x. So in our case, so for example, if x represents time, we're interested in partitioning time into specific partitions. And so for each partition, the sample mean is estimated by taking the average value of y, whose x value lies in the partition. And then we're going to use the Glasso to estimate a sparse precision matrix using a full path of lambda values. So we're going to estimate a graph for various lambda values, and we're going to pick the sparsity or the value of lambda based on the BIC. Okay, just the normal BIC. So how does the DCR algorithm work? I'm going to go through this pictorially. Okay, hopefully this is easier than going through it line by line. So what we do is, so the first step is, again, assume that we have 15 ROIs, 15 time series, okay? So we estimate a graph for the entire time course, okay? For the full path of lambda values, we pick the lambda value based on BIC minimization, okay? So we have some BIC for the whole time course, okay? Some graph and some BIC for the whole time course. Then we split the data into two partitions. Okay, so we split it into 0 to delta, where delta is very important. Delta is going to represent the minimum distance between change points. Okay, so delta is a very important parameter. Okay, so for the moment, let's just assume that delta is 20. So we estimate a graph for the data between 0 and delta along the full path of lambda values, and we pick the lambda or the sparsity of the graph based on BIC minimization. And then we do the same for the data between delta plus 1 to t. Okay, so now we estimate two graphs for the two partitions along the full path of lambda values, and we pick the graph based on BIC minimization. And so for the two partitions, we sum the two BICs. Okay, and what we're going to do is we're going to subtract it from the BIC from the previous calculation. We're going to subtract it from the BIC of this. So we're going to call it a BIC reduction. Okay. So then the next calculation is going to be for data between 0 and delta plus 1, and then delta plus 2 to t. Again, we do the full path of lambda values. We estimate a graph for all the different lambda values, and we choose the lambda or the sparsity of graphs based on BIC minimization. We sum the two BICs and subtract it from the BIC of the entire data set. Okay? And then we just sequence through time. Okay, so we sequence through time in that format. So the last calculation is going to be for data between 0 and t minus delta, and data between t minus delta plus 1 to t. Again, the same format. We estimate graphs for the two partitions along the full path of lambda values, and then we sum the two BICs. And then we subtract it from the BIC of the entire data set. Okay? And then the first candidate split is going to be the maximum BIC reduction. Okay? So if the maximum BIC reduction occurs at time point rho is our first candidate split. And then what we do is we split our data set into two partitions and we run the algorithm again. So it's kind of like a recursive algorithm. Okay? So let's just take a very simple data set. So suppose we have YT is just IID multivariate normal, so we've got 15 time series, so it's of dimension 15, and we've 500 data points, okay? So there's no connectivity, and there's no connectivity change points, okay? So we should see no BIC reductions. So when we run the DCR algorithm, we get BIC reductions, okay? So these would be candidate change points. So in order to perform some inference on those candidate change points, we're going to run a permutation procedure. So I haven't done this graphically. So you've the best of both worlds. I've done the first one graphically and not this one. You can tell me after which one works better. So after finding the first candidate change point rho, what we do is we permute the whole data, we lose the whole structure, and we calculate the BIC, again, of the whole permuted data set along the full path of lambda values. So we estimate a graph for the whole permuted data along all lambda values, and we choose the lambda or sparsity of graphs of the graph based on BIC minimization. So we record this minimum BIC of the whole permuted data set, And then, as you'd expect, we split the permuted data into two data sets, one consisting of data points y of 1 to rho, and the other consisting of data points y of rho plus 1 to t. Okay? And what we do is we calculate the BIC of those permuted data sets along the full path of lambda values separately, and we choose the lambda that minimize the BIC for each data set. And then, of course, we subtract the sum of the two partitions from the data set, from each data set, from the BIC of the whole permuted data set, and we record the BIC reduction, okay? And then we're going to repeat this several times so we get a nice permutation distribution for each candidate change point. And so we repeat then this procedure for each candidate change point, and if the BIC reduction for change point rho is inside these, say, 95% confidence bands, then the BIC reduction is impervious to the time order of the data, and so the undirected graph remains unchanged, so it's not a significant change point, and if it's outside, then it is. So when we go back to the original data set and we calculate permutation confidence bands for the data, or for each candidate change point, we see now that they're nicely within the confidence bands, so there's no significant change point. And so when we estimate a graph for the entire data set, we see that there's no connectivity. Okay? This is just a check. This is correct. So what happens? So in fMRI, we normally have multi-subject data. Okay, so you can think of it as a single subject data. In fMRI, so assume now that we've 20 individuals where they each have multivariate normal time series. Again, it's just IID. We've 20 time series, 20 ROIs, and we have 1,000 data points. So we run this, and what we do is we simply stack each subject on top of each other, so we get some sort of panel data. So we run this, the DCR algorithm on this, it finds no BIC reductions, and we estimate the functional connectivity or the graph. We see that there's no connectivity, again, which is just a check. So this is correct. So if you're interested in multivariate normal, and in the papers, there's lots of simulations on multivariate normal where we add dependence change points. It can detect the dependence change points, and there's lots of different simulations. So if you're interested, I will refer you to the data. But with fMRI, we normally have certain characteristics that are similar to a vector autoregression. So I'm going to move now to the vector autoregression. So we're going to run this DCR on simulated vector autoregression data. So VAR, for those of you who don't know, so it's an econometric model used to capture the evolution and the interdependencies between multiple time series. So a VAR2 model has this form, and it has the property of autocorrelation in the individual time series, as well as possible cross-correlation between the time series, and is just representative properties underlying fMRI, okay? So we're going to run DCR on VAR data and check to see how it performs. So suppose YT is, again, I'm going to switch between single subject and multiple subject. I'm going to do this quite often, okay? So this is single subject, and I'm going to move to multiple subject, and then I'll return back to single subject again. So suppose we just have YT as a VAR with 15 time series and 1,000 data points. And so this is the true connectivity structure. Okay, so it's a very simple connectivity structure. So we've partial correlation, say, between between ROIs 8 and 15, between time points 1 to 500, and then at time point 500, it changes, okay? So the connectivity then is between 2, 6, and 13 for the last 500 time points. So there's one change point here, okay? So when we run, this is the true structure. So when we run, if we didn't run DCR at all, and we just ran it for the whole data set, this is what we'd get, okay? So when we run DCR on it, we get the following, okay? So we get this large spike at time point 500, which you would expect. And then you probably can't see it here, but when you zoom in, so we're going to zoom in into this graph, you get the following, okay? So a few months ago, I gave this talk, and I said, well, what should we do? And the person there in the back put his hand up and said, don't zoom in. So we're not going to do that. We're going to be more worried about what's going on. So there's change points here that we don't expect, okay? So these confidence intervals are based on a permutation procedure. So there's change points here. So the one at 500 is the one we want. Everything else is a false positive. Sorry. Okay. So the permutation procedure, it provides a quick and clean method for computing the confidence bounds. However, if there's serial dependent structure present in the data, it fails to take this into account because it rejumbles all the data. So it thereby incorrectly estimates the confidence bounds. Okay? So a method that is more mindful of keeping the dependent structure intact is the stationary bootstrap, which was introduced by Politis and Romano in 1994. So the stationary bootstrap, it's an adaptation of the block bootstrap that allows for randomly varying block sizes. Okay? So here's a nice picture of what's going on with the stationary bootstrap. So with probability 1 over t, you go into the data set. So in our pseudo time series, the 50th, so we just go in and randomly pick one time point. So we pick this time point, and this is going to be our first time point in the pseudo time series. Then with probability 1 minus p, the next time point in our pseudo time series is the time point in the original time series, and we keep on going like this. So by specifying that p is, say, 0.05, the mean block size will be 20, okay? So what we're going to do now is we're going to, instead of running the permutation procedure, what we're going to do is instead of running the permutation, we're going to run that procedure, but instead of just permuting the data, we're going to be stationary bootstrap the data, which hopefully keeps the dependent structure intact. So when we do that, so the first graph on the left-hand side was with the permutation procedure. And when we do that using the stationary bootstrap, you see that all these false positives are now comfortably within the 95% confidence bands generated by the stationary bootstrap, okay? So all we have now is one significant change point at time point 500. And so when we estimate the graph for that, then you can see that it estimates the correct connectivity structure, okay? So that's for a single subject. What happens if we have multi-subject and we also have a mean change? Okay, so what happens when we have a dependency structure change or a functional connectivity change? We also have a mean change. Okay, so here we have 10 subjects. So and each subject is a vector order regression with 20 time series and 600 time points. And so what happens here is, you're just going to have to trust me on this, but there's a mean change points between time points 250 and 450. So at these time points, we've just added 3 to all the different subjects, okay? But there's also dependency change points at time points 200 and 400, okay? So what happens? So between 0 and 200, there's nothing happens. So there's a dependency change points or a functional connectivity change points at time point 200, okay? And then at time point 250, there's a mean change point. So it detects the mean change point. But if you look at the connectivity structure, it does not change. So between 201 and 250 and 251 and 400, the connectivity structure stays the same even though we have a mean change point. And then the same happens between 400 and 600. So between 400 and 600, the connectivity structure is not changing. But there is a mean change point. So it detects the mean change point at time point 450, but the connectivity structure does not change. So it detects the mean change points, but for us, they're not really of interest. But we have to calculate these in order to get the correct connectivity structure. So what else can happen? So suppose we have 10 subjects, and each subject is a var with 20 time series and 1,000 data points. And then we simply just have 5 subjects who are noise. Okay, so you can think of this as we have 10 subjects who are behaving in a very nice way, and then 5 subjects who are just noise. Okay. So what happens? So when we run DCR, it finds the correct connectivity change points for the people who are in the var structure, and it also finds their connect connectivity structure. Okay. So here, there are some simulations. Again, there are a lot more simulations in the papers. We kind of go mad in simulations in the papers with variance changes, with spikes, with lots of different things. Okay, so if you're interested in the simulations for var data, I'll refer you to the paper. So the last simulation is as follows. So simulation 6 is again with var data, but instead of just doing one iteration, we carry it out 100 times. Okay, so we have 20 subjects. Each subject has 20 time series and 1,000 data points, and there's 4 connectivity change points. Okay, and we run this, repeat this 100 times. So in each case, all 100 connectivity change points were found, but also 4 false positive change points were found. But for each false positive, the correct undirected graphs are found before and after. What I mean by that is that if a false positive was found at, say, time point 700, if we estimated the graph between 601 and 700 and 700 and 800, it found a graph that was very similar to all the data between 6 and 800, okay? And then when you look at the number of times it finds the edges, it performs very well, okay? So these are just percentages of how many times it detects the edges in each partition or for each data sequence between each pair of significance change points. Okay. So what I haven't shown here is we also compared it to the log likelihood ratio test, and it outperforms that as well. But again, I haven't shown it here. I'll refer you to the papers as well. So just going back to the experimental data set, where the subjects were told that they would need to prepare, they'll be given 2 minutes to prepare a 7-minute speech. So this data was taken from an anxiety-inducing experiment. So from Wager et al. In 2009 and Lindquist and McKeague in 2009. And so during the course of the experiment, we had 250 images were acquired. So we have 215 time points. And so we got 2 separate data sets were extracted from the experiments. We had one with 4 regions of interest and heart rate for 23 subjects. And we had 5 regions of interest for 26 subjects. And there is some overlap between the ROIs. So we wanted to see if the DCR could be used to test whether the onset of stress was associated with changes in the connectivity between the brain regions and between heart rate and brain regions. So here are the regions of interest. And so when we ran DCR, we got the following change points. So if we run no algorithm, and I asked you all to look at the experiment and guess where the change points would occur, you'd probably say, well, it's going to occur where the visual cue, first visual cue where they're told the topic. And the second one would be where they're told that they don't have to give the speech at all. So without running any algorithm, this is what you'd probably guess. So when we run the DCR algorithm, and we run the stationary bootstrap to find the significant change points, we see that there's 2 significant change points, okay? So there's 2 significant change points. And they're exactly where you'd probably guess they are. They're around the speech instruction slide and then the no speech instruction slide, okay? And then when we estimate this is for the multi-subject data, so when we estimate the graphs, this is what we get. Then for the 5 regions, we get a lot more change points. We get the change points around the speech instruction And we also get the change point around the no speech instruction. But we also get other change points as well. So you can think about the first change point here is probably something to do with anticipation. They're probably changing state. And then the other ones here are different states as well, while they're thinking about their subject, and maybe they're different states while they're relieved and relaxed at the end. And then when we estimate, so here I think we had 8 significant change points. So when we estimate the graphs, this is what we get. Okay, so that was kind of like the first work. We decided to attack the multi-subject data in the first paper. In the second paper, we extended this DCR methodology in 2 ways. And we focused here on the single subject data, okay? So what we did is, I'll just show this with some chalk. So if we ran the DCR algorithm, so assume that this is time. And so because this algorithm is recursive, so if we say this was 0 and this was 215, so if the first change point that was found was, say, somewhere in the middle, and we got a BIC reduction, okay? This BIC reduction calculation is assuming that we find no further splits or further change points. So if we found another change point, say here, this BIC calculation is not really accurate. Because first of all, it was partitioning, say, 0 and 100 and 101 to 215. But now what it's doing, because we find this change point here, it's now only partitioning this partition and this partition. So the BIC calculation here is not accurate. So what we do is once we allow the algorithm to go through, we go through time again, and we recalculate the BIC for a more accurate estimation of the BIC. So we recalculate the BIC so that there's a few things we add. So we recalculate the BIC reduction at each candidate change point to obtain a more accurate estimate. And obviously then our stationary bootstrap procedure slightly changes as well. And then because there's the issue of the false positive edges estimated by the graphical lasso, we introduce a bootstrap inferential procedure on the edges. This is similar to the subsampling procedure of Menshuisen and Buhlmann. I hope I pronounced them correctly. And the issue of false positive edges estimated by the graphical lasso in the subject is dramatically worse in the single subject case. Okay. So I'm going to show you why we need this extra bootstrap procedure. So suppose, again, we've left the multi-subject case. I'm moving to the single subject case. So suppose YT is a vector autoregression with 15 time series and 500 time points. Okay, so this is the true connectivity structure changing over time. Okay? So when we run the DCR algorithm, you can see that there was 5 graphs, so there was 4 change points. So when we run the algorithm, you can see that it finds the 4 change points. Okay? And so what I do here is, this is the truth. This is the actual graph. These are the graphs estimated by the Glasso without the bootstrap procedure. Okay? So you can see in some of the graphs, so especially say this, whoops. So especially here, so in the second graph, you can see that it estimates a lot of false positive edges. And say in the fifth one here, there's a lot of false positive edges. Okay? So when we run the extra bootstrap procedure on these graphs, we get the following. Okay? So you can see that it certainly cleans up the graphs to a large extent. So we're comparing now the last row to the top row because the top row is the true graph, are the true graphs. Okay. So what we did then is we went back and we went back to the experimental data set And with this new DCR algorithm, we estimated change points for each subject individually now, okay? So here we have so on the y-axis we've got each subject, on the x-axis we've got time, and so you can, on each of these little x's or crosses represent significant change points, okay? So you can see that each subject has a change point around the first visual cue. And then the pattern changes to some extent. So some subjects have a second change point around the second visual cue, some have it before and then after, so it's not the same pattern, okay? So what we did was we estimated graphs for the first partition, okay? Just to see how variable the graphs are in each subject. So we estimated graphs for the first partition, so between time points 1 and the first significant change point for each subject. And we get the following, okay? So these are for the 23 subjects. And we just, by analyzing each subject individually. So you can see that there is some similarity, okay? So they all have positive partial correlation between ROI 1 and 2, but then there are things that are quite variable, okay? So the question is, so if we've multi-subject data, how do we combine? Okay. So the multi-subject DCR, it sort of averages the connectivity across the group. But by doing this, the group average results may belie the unique activity patterns of individual subjects. And by analyzing individual subjects, we may be able to determine if an individual scan is normative with respect to the reference population, okay? So the single subject DCR allows us to understand the sources of inter-subject variability in brain activity, okay? So there are the two algorithms that we've published. We're now writing up, I'm sorry I couldn't present it here, but we have a new method that sort of jointly, so we sort of use the information across subjects. We just don't simply take an average. And that it jointly estimates multiple graphical models by exploiting the similarity between subjects' brain networks. So it kind of takes the best parts of both. We analyze them all together, but at the end of the day, we will get individual graphs. Okay, so I know this is biological week, but I'm going to switch now to a couple of slides on finance, okay? So is it robust? So suppose YT now is an IID multivariate T distribution time series where we've got 20 time series and 1,000 data points, okay? So what happens when we run the DCR algorithm on this? So when we run the DCR algorithm, we get the following plot. So you can see that it does find BIC reductions, but none of them are significant. And then when we estimate the graph, again, this is multivariate T distribution, we get no connectivity structure, which is correct. So I'm not going to show you any more simulations, but we've done a lot of where multivariate T simulations where the dependent structure is changing. It has a dependent structure and it is changing. And the DCR algorithm works quite well. So we applied this to financial data. So we applied this to the Dow Jones. So these are daily returns of the Dow Jones, the S&P 500, the NASDAQ, the Russell 2000, and then the percentage change in the 10-year bond interest rate, okay? So we applied the DCR to this, and we got the following plot, okay? So it found lots of change points, and so then we tried to sort of align the change points with things that happen in finance. So some of these change points can be linked to real events in the stock market. So in this change point here, so in 1997, this guy, large guy here, so in 1997, the Dow Jones, so on October 23rd, 1997, the Dow Jones posted its worst one-day points loss ever. Then in 2003, between March 20th and April 14th, we had the invasion of Iraq, which may be pertinent to the change on April 21st here. And then in the financial crisis, so in September 2008, the US government took over Fannie Mae and Freddie Mac. On September 14th, Merrill Lynch was sold to Bank of America. On 15th, Lehman Brothers filed for bankruptcy. So this may be related to the change point around here, even though it's quite small. Okay. So to summarize, so dynamic connectivity regression, so it's an approach for splitting the experimental time course in a functional neuroimaging experiment into partitions based on functional connectivity changes between ROIs. We have two algorithms now. We have a single subject and multi-subject DCR. I haven't shown all the simulations, but there are lots. So simulations show that the method is robust to the addition of spike artifacts, mean and variance changes that commonly occur in fMRI data. And the addition of noise and weaker signals do not affect the results. So, of course, can DCR be applied to a lot of the fMRI data? The short answer is no. Most fMRI data series, the events are happening quite quickly, okay? So DCR, as I talked about at the start, it relies on this parameter delta. So delta is the minimum distance between change points. So through simulations, we found that delta needs to be large enough in order to get stable estimates of our mean and covariance. So the smallest delta that we can work with in the multi-subject case is around 15 to 20 data points. So in fMRI, these events are happening much quicker. So in most cases, this DCR is not going to be able to be used, okay? But where could you use it? So it could be used on resting state data. So hopefully these transitions, but our states are happening slower. Or data of aha or eureka moments. Okay, so you can imagine that somebody's in a scanner and they're trying to solve a mathematical puzzle, or they've got a chessboard and they're trying to work out some things. And we'd like to see, well, what is the connectivity coming up to that moment? We don't know where that moment occurs, and what happens, so coming up to that moment, that's essential. Okay? But we don't know where that change point occurred. We're also applying it to pain data and data from hallucination experiments. Again, we don't know when the hallucinations are occurring. So hopefully these transitions are slow. And we're hopeful that this is the beginning of further work in the identification of emotion, stress, or resting state transitions, and aberrant connectivity patterns. And then this is a long shot, but we hope the methods will assist our understanding of the human brain and neurological disorders such as depression, Alzheimer's, and the treatment of these disorders. So what are the future directions? So we're beginning to work on a Bayesian DCR, so it's incorporating scientific hypotheses by means of a sparse prior distribution. It'd be great if we could incorporate structural information using, say, DTI, where we can see whether two regions are linked through their fibers. And then something that also might be of interest is linking these change points and network structures to behavioral data through ergoms or something like that. Okay, so finished a few minutes early. So the collaborators, so my advisor, Martin Lindquist, Tor Wager, Lauren Atlas, Ragnar, who's at Columbia. And these are some of the references. So thank you.
Questions? Did you check how robust it would be if ever there was one variable that you do not observe that is still correlated with the other one?
Yeah.
But you miss it for some reason?
Yeah, no, we haven't tried that. But that, yeah.
Because you had very big differences at some point, depending on whether you were taking 4 regions and heartbeat or 5 regions? So
those regions are not they're not the same. So those 4 regions, just go back, you can see that they're not exactly the same. So it's not just 4 of the 5 regions and heartbeat. So there's some overlap, but they're not exactly the same. But yeah, we haven't tried to see if there's another latent, you mean like a latent variable?
For
Yeah.
me, it's a heartbeat in the second state, and you have in the second example, and you have many touch points. It's just because it changes in the heartbeat or something like that.
Yeah, well, the heartbeat was with the one that only had 2 change points.
Yes, when
So
it was in it.
Okay, so if you put the heartbeat into the 5 otherwise, yeah, we should try that. Yeah, we're trying to move away from this data set because so many people have used this data set. But yeah, we could try that.
Now you're comparing in your change point setup always the first part of the data set with the second part of the data set, which has advantages and disadvantages, particularly in the multiple change situation. Have you tried going through with a moving window kind of thing where you compare delta and delta?
We haven't tried that. Again, we tried to move away from the moving window as well, but we could try that for sure. Because I'd like to see if I had time or a master's student maybe to do that and to compare them if to see which one performs better. I think that's a great idea.
Well, I mean, it will depend on the situation which one performs better.
Exactly. Yeah. Yeah.
So you're probably
But then the length of the window becomes an issue, like the delta
but
here.
the length of the window is exactly the same issue. It should be as long as possible, but short enough so that only one change point is in it. Yeah, ideally, it should be the length between the smallest length between 2 change points.
Yes. Yes.
Or actually, ideally, at whatever location is, you want to go to the right to the next change point and to the left to the next change point.
Yes. Yeah.
You cannot do it, but that would be what you want.
So in the end, you're only looking for one change point. You never look at 2 change points at a time.
No, so yeah, that's correct. So it's just one change point at a time. We could partition instead of just looking at 2 windows. You could do it like in 3 or 4 and so on. Yeah, that might be better. That's something that was suggested before as well. Yeah. So instead of 2 partitions, you have 3 partitions. Yes. Yeah.
But then, for example, you may face the problem that when you want to put 10.
Yeah. Yeah, Claudia.
And for the financial example in 2008, I mean, you said that it was a very small change point. Could it be that it's just so many different bursts of strange things happening?
It could, and there was 2 change points found around there as well.
Yeah.
So yeah, it could be due to that. I mean, it's just a small BIC reduction. Yeah. It could be due to that as well.
So when you have lots of things happening that are within your deltas, what happens in that case? Have you tried to see?
So you mean, so just say that they found these 2 change points first?
Well, I just imagine that there's I mean, at that time there was just a crazy amount of volatility.
So we're not going to be able to capture all of them.
No.
So it's going to find the one with the largest BIC and that's it.
Yeah.
So I mean, maybe we could do some sort of confidence around the change point as well. Yeah, that was suggested as well. Yeah.
Why didn't you go back a little farther?
Sure.
In time, no, for that.
Oh, sorry.
Can you go back to, say, 1995 or 1990? The data have to be there, and there were a couple of things that happened in 1997 and 2001.
Yeah, so we captured 97. So this is 97. Yes, yeah. So 1987 was something else.
But 2001, there was a big meltdown too.
Yes, so I think some of these refer to, these will be around 2001 as well. But I haven't put in all the events in this. There are other events, and some of them aligned and some of them didn't. But there are other events, and it is in the paper, but I only selected a few, yeah.
Right, well, I noticed you said that the change points that you observed seem to be tied to turmoil in the world somewhere.
Exactly.
But you didn't say that turmoil in the world somewhere is always tied to a change point.
Yes. Yes, yeah.
I have a question concerning the bootstrap procedure. So using the stationary bootstrap seems reasonable for your data because it's more robust, right?
Yeah.
But if you do believe in your vector autoregressive model, why don't you just use a kind of residual-based bootstrap based on that model?
So sorry, say that again?
Well, I mean, the natural thing to do with a vector autoregressive model is to use an AR bootstrap kind of thing. Or because there's some problem with doing it auto-regressively, you could do a regression or pair kind of.
So you mean fit a vector autoregression to the data?
Pretty much, yeah.
Yeah, I mean, that's also possible. Yeah.
So there are some variations.
Yeah, for sure. I'm not saying that this is the only way. I mean, there are lots of different ways. This is one way. Yeah.
Right, any further comments?
Yeah, Peter?
Moving on to the Bayesian, is there some thought about that you could use your procedure to give you some idea of proposals?
Proposals for...
For thinking about sampling change points. So I mean, if you're going to a fully Bayesian, you know, what you've done here, does that give you some information about building good proposal distributions for change points?
So running this and then you... Oh, yeah, so... I mean, we were thinking about it like differently, the sparse prior using information that, say, the scientist gives us that they'd expect it here or we'd expect this connectivity. So that's, but yeah, you're thinking it from the other way around. So using this.
Because it's very fast, yes? No.
It's,
It looks
so,
like it was fast.
so it is fast. I mean,
relative to what you're having to do in a Bayesian procedure.
Exactly. So it is fast. So yeah, you could run this and then use that information in a Bayesian. We were thinking it from the other perspective, getting some information from the scientists and using that information. Yeah.
I was thinking more from the proposal rather than pushing it into the prior one. Yeah.
Okay. Okay.
Just one quick comment, Ivor. So in the picture where you had 23 subjects
Yes.
for the fMRI data, and then you had there's like group-derived change points.
Yes.
And then you look at the individual subjects, there's a bit of a variability.
Yes.
It'll be interesting to also characterize that variability around these change points. So maybe Bayesian maybe might be a way to do it.
Yeah.
And in fact, you were qualitatively saying that the first change point was more or less consistent across subjects, but the latter ones are a bit more of a variability there, a lot more uncertainty as to where that happens.
Yeah. Okay. Right.
Any further comments? Questions? Right. No, just please join me to thank Ivor for very, very nice.